Your brain's wires, the secret life of neurons. Think of your brain as a city, a metropolis that never, ever sleeps, buzzing with activity, day and night. It's packed with billions of residents, all rushing around, carrying vital information, making decisions, and keeping the whole place running. Now, what if this city was powered by a massive, intricate grid of living electrical wires? A network connecting every single building, every street corner, every traffic light. Well, your brain has somewhere around 86 billion of these wires, roughly the same number of stars in our galaxy. But these aren't just any wires. They're living cells, the fundamental building blocks of your nervous system. They are your neurons. But how do these biological wires actually work? How can a single, microscopic cell zap a message with enough speed and precision to make you snatch your hand from a hot stove before you even consciously feel the pain? And how can trillions of these tiny connections let you remember your first day of school, hum a tune, or even understand the words you're hearing right now? Today, we're going to zoom past the skyscrapers of the brain city and get personal with just one of these electrical wires. We're going to uncover the secret life of the neuron. By the end, you'll get the elegant, ingenious design that makes you, you. To really get a neuron, you have to think small. Unbelievably small. A tiny piece of brain tissue the size of a single grain of sand can hold as many as 100,000 neurons and 1 billion of their connections. So, let's shrink way, way down to their level. What we'd see looks less like a simple wire and more like a bizarre, beautiful tree. This is our hero for the day, a single neuron. And just like any city worker, our neuron has a specific job. It's a messenger, a tiny courier carrying signals from one part of the brain city to another. Some, called sensory neurons, are like field reporters, bringing in intel from the outside world, like the feeling of a cool breeze on your skin. Others, the motor neurons, are the delivery drivers, carrying instructions out from the brain to your muscles. And then you have interneurons, the crucial go-betweens, passing messages from one neuron to another. But no matter their job title, all neurons are built with a similar game plan. They are designed for one thing above all else: communication. And to communicate in a city as complex as the brain, you need specialized gear. You need a way to receive messages, a head office to process them, and a high-speed delivery route to send them on. The neuron has all three. Let's check out the anatomy of our hero. First, you'll notice a thick, central hub. This is the soma, or cell body. Think of it as the neuron's command center. It holds the nucleus, which contains all the genetic blueprints, and it's where all the energy is generated to keep the cell alive and firing. It's the metabolic heart of the operation. Sprouting from the soma are these dense, branching fibers that look just like the limbs of a tree. These are the dendrites. The word dendrite literally comes from the Greek for tree, and it's a perfect fit. Dendrites are the neuron's antennas. They're covered in thousands of tiny posts, eagerly listening for incoming signals from other neurons. This tree-like structure lets a single neuron tap into thousands of conversations at once, gathering a huge amount of information. Then, snaking away from the soma, is one very long cable. This is the axon. If dendrites are the ears, the axon is the mouth. This is the transmission line, designed to carry the message away from the command center and pass it on. And some of these axons are shockingly long. The longest neuron in the human body is part of the sciatic nerve, a single cell that stretches from the base of your spine all the way to your big toe, can be over 3 feet long. At the very end of the axon, it splits into a bunch of smaller branches, each ending in a little bud called an axon terminal. This is the final stop, where the message gets handed off to the next neuron in line. So we've got our structure, dendrites to receive, the soma to process, and the axon to send. But what about the message itself? How does it actually travel? This is where things get electric. This signal is called an action potential. The secret to a neuron's incredible speed is its ability to create and send an electrical signal. This signal is called an action potential, and it's the fundamental currency of information in your brain. Think of our neuron like a tiny charged battery. When it's just sitting there, not firing, it maintains a small negative electrical charge. There's a delicate balance of positive and negative ions, mostly sodium and potassium, on the inside versus the outside of the cell. This creates a state of electrical tension, like a coiled spring, called the resting potential. Now, let's say the dendrites get a flood of incoming signals. These signals are actually chemicals that start opening tiny gates in the neuron's membrane. As these gates open, positively charged sodium ions begin to rush into the cell. If enough signals come in and enough gates open, the charge inside the neuron hits a critical tipping point, a point of no return. This is the threshold potential, which sits at about 55 millivolts. Once that threshold is crossed, it triggers an unstoppable chain reaction. Bang. Suddenly, all the voltage-gated sodium channels in that area fly open. Sodium ions pour into the axon, causing the inside of the cell to become momentarily positive. This is the action in the action potential, a wave of electricity that zips down the axon. It's an all-or-none event. The neuron either fires with its full strength, or it doesn't fire at all. There's no half fire. It's like a wave at a stadium. Once one section stands up, it triggers the next, and the wave shoots down the line in one direction. Immediately after firing, the neuron slams the door on sodium and pumps positive ions back out, resetting itself so it can fire again. This electrical wave, this spark of light, travels down the axon. But in the brain, fast isn't good enough. You need to be ridiculously fast. And for that, the neuron has a secret weapon. For many neurons, especially the long-distance messengers, the axon is wrapped in a fatty substance called the myelin sheath. But this sheath isn't a solid tube. It's segmented, like beads on a string, with tiny, uninsulated gaps in between. These gaps are called the nodes of Ranvier. Myelin is an amazing electrical insulator, kind of like the rubber coating on a wire. It's produced by helper cells, oligodendrocytes in the brain and Schwann cells elsewhere. This insulation prevents the electrical signal from leaking out. Because the axon is insulated, the action potential doesn't have to regenerate at every single point along the way. Instead, the electrical current zips passively under the myelinated parts and is then powerfully recharged at each exposed node. The action potential literally jumps from one node to the next. This incredible process is called saltatory conduction, from the Latin word saltare, which means to leap. This leapfrogging makes the signal insanely fast and efficient. While signals on unmyelinated fibers, like those that carry a dull, throbbing pain, might poke along at 1 or 2 miles per hour, signals on myelinated axons can rocket along at up to 268 miles per hour. That's faster than a Formula One car at top speed. The estimated 100,000 miles of these myelinated superhighways in your brain are what make you react, think, and feel in an instant. Our signal has just raced down the axon at incredible speed and reached its destination, the axon terminal. But now it faces a problem. Neurons don't actually touch each other. There's a microscopic gap between the end of our neuron and the dendrite of the next one. This gap is called the synaptic cleft. So how does the electrical message cross this chasm? It can't jump. Instead, it performs a beautiful little magic trick. When the action potential arrives at the axon terminal, it triggers the release of tiny chemical messengers called neurotransmitters. These chemicals, stored in tiny sacs, are dumped into the synaptic cleft. They float across the gap and bind to specific receptors on the dendrites of the next neuron, like a key fitting into a lock. This connection either excites the next cell, pushing it toward its own action potential, or it inhibits it, telling it to stay quiet for a moment. This is the grand finale. The message is converted from electrical to chemical and back to electrical, allowing the signal to continue its journey. Your brain contains up to 100 trillion of these synaptic connections, a network of unimaginable complexity. We've journeyed into the microscopic world of a single neuron. We've seen its tree-like branches, its electrical spark, its insulated highway, and its chemical handshake. Now let's zoom all the way back out. Every single thought you have, every memory, every emotion, every action. It's all the result of these tiny signals firing across trillions of connections. When you decide to lift your arm, a cascade of neurons fires from your brain, down your spinal cord, and out to your muscles in a fraction of a second. When you see a familiar face, a specific pattern of neurons lights up, drawing on stored connections to give you a name and a feeling. Learning something new is literally the process of strengthening the connections between neurons, carving new pathways in your mental city. The neuron is a masterpiece of biological engineering. It's a wire, a battery, a receiver, and a transmitter, all rolled into one. The secret life of the neuron isn't just about ions and chemicals. It's the story of how we think, feel, and live. That bustling city inside your head is built from these incredible secret wires. Exploring the neuron is just scratching the surface of the mysteries inside our own minds. If you're as fascinated by this stuff as I am and want to explore more of the brain's hidden neighborhoods, make sure to subscribe and turn on notifications. There is so much more to discover together. Thanks for watching.